digital systems deal with zeros and ones. We're able to group a collection of zeros and ones, or specifically a collection of wires, each wire carrying a 0 or 1. We can group a bunch of wires together and think of it as representing a single number. We do this so humans can understand what the system is doing, or conversely, so that we can implement specific algorithms in digital hardware in a convenient way. Usually what we do is we simply convert our number to binary to represent it. So the number 12 in binary is 1100, the number 3 is 0011, the number 9 is 1001. We have a choice of where the most significant bit goes and where the least significant bit goes. Humans normally write it most significant bit on the left, least significant bit on the right. And so in this case, if we want to store the number 12, we'd have 1100. So 4 wires, the first 2 wires contain 5 volts or a high level. The last 2 wires contain 0 volts or a low level. For 3, 0011. For 9, 1001. This, however, is somewhat arbitrary. We could have come up with a completely different encoding. It just would have been less convenient. The limitation of this is that we can't store negative numbers, but there's an easy solution, and that's what's known as 2's complement, which we're going to talk about in this video. It's not the only way of storing negative numbers. There are different representations, but arguably 2's complement is the most convenient way of doing it. The challenge is to work out how to store the numbers -3, -1, 3, etc. using, for example, 4 bits. Once again, there's an infinite number of ways of doing this, but the convenient way of doing it is using 2's complement. For reasons that will be explained shortly, we're going to store the number -1 as 1111. The number 3 is stored as usual, 0011. So positive numbers are stored as usual. However, because we have to fit in room for negative numbers, the largest positive number is limited. So if we had 4 bits, then traditionally we could store numbers from 0 to 15, but we're going to be using some of this range to store negative numbers. So in fact, in 2's complement notation, in this particular case with 4 bits, the largest positive number we can write down is going to be 0111, which corresponds to the number 7. The number -3 is going to be 1101, and we'll explain why presently. Right now, the key point is, on the left, we have the representation used in a digital system, what is physically carried by the wires, and on the right is how we humans interpret what is being stored. Because FPGAs are not human, they don't use the numbers here, at least not explicitly. They're not thinking like humans. FPGAs simply do what they're told. If the FPGA is told to add 2 numbers together, it can't do that. It needs Verilog code that tells it how to manipulate these bits using lookup tables and flip-flops. So it's Verilog and Quartus that synthesizes the Verilog code into the FPGA's hardware implementation. That's what needs to understand that when we have certain bits in certain registers, then us humans want to interpret them as corresponding to these numbers, and if we ask Verilog to add these 2 numbers together, then it's Verilog and Quartus that has to figure out that, okay, if this has got this bit if this has got this bit pattern in it, then this number is -3. If this has got this bit pattern in it, then this number is -1. And if we want to add them, then we get -3 plus -1, which is -4. And so the answer needs to be whatever the bit pattern is that corresponds to -4. The great thing about 2's complement is that if we use an ordinary adder to add these 2 numbers together, then in fact we're going to get the correct answer of -4. We'll explain in greater detail presently why that's true, but for now, for fun, let's just do this addition. So if we take this number, 1101, and this number, 1111, and we add them together normally, 1 plus 1 is 0 carry 1, 1 plus 1 plus 0 is 0 carry 1, 1 plus 1 plus 1 is 1 carry 1, 1 plus 1 plus 1 is 1 carry 1, and because we only have 4 bits, then anything over here just gets chopped off, and so our answer is 1100. And as we'll see presently, in 2's complement, 1100 actually represents -4, so we've obtained the correct answer. If we have a 3-bit number, then if we were to add 2 and 3 together, we'd get 5, that's fine. If we add 5 and 4 together, we get, well, technically we get 9, but 9 won't fit in here. So what do we actually get? We'll get 5 plus 1, 2, 3, 4. We get the number 1 in here. So due to having only 3 bits, we're going to overflow, but basically what we're implementing is clock arithmetic, or we get the answer modulo 8 in this case. If we now want to be able to represent negative numbers, then the trick is to say that, well, just before 0 comes -1, just before -1 comes -2, just before -2 comes -3, just before -3 becomes -4, but if we're not careful, I can fill this up with all negative values and I can't represent any positive values. So we want to stop approximately halfway. And in this case here, halfway is somewhere between the 3 and the 4 mark. What I have drawn is actually the 2's complement representation of a 3-bit number. For example, if I want to store the number -2 using 3 bits, then I see that, well, actually, I'm going to store the number 6, which in binary is 110. So 110 stands for -2. One can ask, why not stop at -3 and allow us to store the number 4 there, because that's also at the halfway mark, so to speak. And the answer is that by doing it this way, a key property is that the most significant bit will be a 1 if the number's negative, and it will be 0 if the number's positive. So to elaborate on this, consider the 2 extremes. If I've got 0 here and 1 here, well, this is the largest positive number. It's positive because this is 0. It represents, in the usual representation, the number 3, and indeed 3 is the same as 3 in this case. For the largest negative number, that's always going to be 1 followed by all zeros. The leading 1 means it's negative by our convention. And so in this case, the usual number here would be the number 4, and we see that storing a 4 actually corresponds to the number -4, which is the smallest negative value we can write here. So by choosing to stop at -4, it allows us to have the most significant bit represent the sign of the number. There is a simple rule for converting a number to or from 2's complement. Let's first look at how to convert a number to 2's complement. We need to know how many bits to use. So if we want a 4-bit 2's complement number, then if we're given a positive number, that's easy. We just write it normally. So 5 using 4 bits is 0101. The only thing to check is that the most significant bit needs to be a 0. If not, we don't have enough bits to fit this bigger number in here. So the number 5 can be stored as a 4-bit 2's complement number, but it cannot be stored as a 3-bit 2's complement number. It's just too big for a 3-bit 2's complement number. If our number is negative though, then we use the following rule. -3, we first of all write 3, positive 3 in binary. That would be 0, 0, 1, 1. We then flip all the bits. That gives us 1, 1, 0, 0. And incidentally, this is called the ones complement representation. To get the twos complement representation, we just add 1 to it. So we get 1, 1, 0, 1. And this is the twos complement representation, 4-bit wide, of the number -3. Let's do it for -8. Write 8 in 4 bits, 1, 0, 0, 0. Invert all the bits, 0, 1, 1, 1, and add 1. That gives us 1, 0, 0, 0. So this is the twos complement representation of -8. To go the other way, we could invert these steps, which would mean subtract 1 and invert all the bits. But it turns out that we just have to apply the same thing, and it works, because the inverse of this operation is just applying the same operation. So for example, if we're given 0, 1, 0, 1, what do? Well, the first thing we do is we look at the most significant bit. Because the most significant bit is a 0, we know this is a positive number, and so we just convert the rest of the number into decimal. So 101 in decimal is 5, so we know this represents the number 5. 1010, look at the leading bit, it's a 1. That means it's a negative number. That means we have to apply this procedure over here. So we first invert all the bits, 0, 1, 0, 1. Then we add 1 to get 0, 1, 1, 0. Then we convert this to decimal. So we've got 1, 2, 4. 2 plus 4 is 6. So that represents the number 6, or this represents the number 6. But this one, because it's negative, represents the number -6. For this number here, we see it's a negative number, therefore we invert all the bits to get 0, 0, 1, 1. We add 1 to get 0, 1, 0, 0. This is the number 4, which means this represents the number -4. Finally, for this one, the leading bits are 0, so it's a positive number. So we just look at these 3 bits and we see that we've got the number 6. To emphasize, it just so happens that by doing the same thing, inverting all the bits and adding 1 works in both directions. It's a very special property of twos complement notation. To summarize, twos complement notation works because we are just doing clock arithmetic. We take our clock and we replace some of our numbers with negative numbers, then usual addition still works. We choose the point at which to divide between our negative numbers and our positive numbers so that the most significant bit tells us the sign of the number. If the most significant bit is a 1, then it's a negative number. If the most significant bit is a 0, then it's a positive number. This, of course, means that the largest positive number will be 0, followed by however many 1s we need to make up the number of bits in our representation, and the smallest negative number is going to be 1, and then however many zeros we need to make up our representation.